Hello everyone, we're Team 8 and we're excited to share with you our haptic feedback digit prosthetic. My name's Alisha and this is Zach, Gary, Ian, and Michelle, and we are the team members of Modulo Prosthetics. So to start off, we want to introduce you all to one of our patients whom we're going to call Joe. Joe is a 32-year-old firefighter born in Clifton Heights, Pennsylvania, who lost 60% of his middle, pointer, and thumb due to a fireworks accident in 2013. After undergoing numerous digit lengthening procedures for over 2.5 years, Joe still found himself unable to do much of his everyday tasks. He can no longer play golf with the sun, button up his shirt by himself, and eat his favorite Chinese food with chopsticks. While he considered prosthetics, he found that none of the devices currently in market matched the level of comfort and functionality he needed to get back to doing what he loved. Joe is among one of the 45,000 people who undergo partial hand amputations every year. These injuries are most common among middle-aged males as a result of crushing injuries, stab wounds, and manual labor injuries, and they result in significant debilitation in everyday life, especially when they involve a partial amputation of the thumb. Namely, partial hand amputees can experience about 40% loss of overall hand functionality, about 94% experience some form of stress or anxiety-related mental health issue, and a significant proportion end up changing their jobs or careers due to the limitations posed by their amputations, including a staggering 25% who end up quitting the workforce in its entirety. So despite their high level of occurrence and level of impairment, prosthetics as a form of rehabilitation for this type of injury are highly underutilized. One of these reasons is due to the ease of delivery. Because of their highly customizable nature, prosthetics can take anywhere from 6 to 8 weeks to be delivered to the patient, leaving an often unbearable amount of time between when they receive their injury and when they receive any form of tangible support. Another inhibiting factor is the financial barriers. Prosthetics can range anywhere from $5,000 to $70,000 per digit, and more often than not are not covered by any form of insurance. Lastly, the current devices in market do not contain any form of sensory feedback, limiting the patient's ability to perform any of the fine motor movements that we often depend on our fingers for.
After discussing with prosthetic and rehabilitative specialists as well as end users, we came up with 4 main pillars our device needs to uphold. The first involves a greatly reduced cost that reduces the financial barriers to obtain a prosthetic that is reasonable for out-of-pocket and or insurance-covered fees. The second involves the adjustability of the device, so that we are minimizing the production time while maximizing the amount of base users that can use the same base device. The third involves the mechanical capabilities of the device, so it's able to withstand the typical pinch and grip strengths that are necessary for completing activities of daily living. This leads to our final and most important tenet of restoring these activities of daily living, which we will assess using the disabilities of the arm, shoulder, and hand questionnaire, which measures the social and physical ramifications of one's disability on a scale of 0 or no disability to 100 or the most severe disability. With these guidelines in mind, we have developed a modular haptic feedback prosthetic that's primarily body powered. That is to say that the device completely relies on the residual movement of the residual digit. In a general use case of this device, the same general paradigm follows, and it all begins with the user's intent to perform some action with their hand. With the device comfortably strapped to the metacarpophalangeal joint of the thumb, the user can move the residual digit, turning this prosthetic into a bending motion similar to that of a normal thumb. But to better control the amount of force that they are applying with this prosthetic, we have embedded a force sensor underneath the tip of this prosthetic that is then connected to a secondary battery-powered microcontroller that drives a vibration motor. By modulating the strength and frequency of this vibration, the user will be better able to discern between the amount of force that they're applying in their everyday tasks. These haptics will allow the user to adjust their movement in a cyclical nature, thus optimizing the performance in their task.
So throughout our design process, our mechanical system has been heavily informed by this crossed 4-bar linkage system here, which allows us to mimic human thumb motion. Through this, the user can actuate the thumb tip by bending the remaining joint when attached to the prosthetic. In our initial iterations, we used straight bars to connect the prosthetic base to the thumb tip, and as well as dowel rods at each joint to hold the system together. However, during movement, these straight rods would get in the way of the user's thumb, and the dowel rods would slip out of their casings. These problems have inspired our current design, which lofts curved bars above the user's amputation site, giving them ample clearance to use the device without obstruction. Further, at the joints, we use a screw and nut pair to secure the rods from both sides to prevent slipping, while still allowing free rotation about the screw for prosthetic movement. While initial prototypes in 3D printed PLA and ABS were great for testing device changes, they were relatively weak materials and were not fit for everyday use. In our current version, we transitioned to using 3D printed Ultim, which offers great material strength while still allowing the device to be 3D printed, which keeps production very easy. We've also made another version in a 3D printed autoclavable material, sorry about that, which is incredibly useful for rehab settings where the prosthetic can be used for multiple patients and be easily cleaned between uses. We've also conducted, to better understand the strength of our device, a finite element analysis in SolidWorks. Here we can apply loads across the device and then see the reaction on the device. We simulate a 10-pound force across the thumb tip here, and this allows us to mimic grabbing an object. Here, by the change in coloration, you can see that the most stress occurs on the rods and the joints towards the back plate. But however, these stresses are below the ultimate tensile strength of the ultim, so the material will not fail in such a task. We were also able to validate these results using a crush test, which we'll show on the right. And the great thing here is that the prosthetic will fail at points predicted by the simulation when a heavier load is applied, so we can see that this is very useful to us.
We've also made iterative improvements to our prosthetic straps at the wrist, finger, and residuum sites. For materials, we tried things such as elastic ribbon, coiled metal wire, and cloth. So in previous versions of our prosthetic, only the wrist strap was adjustable. So in order to better meet our design goal of having a one-size-fits-all prosthetic, we completely redesigned our straps to utilize Velcro, which allows the user to modify the prosthetic to better accommodate their hand. And we found that Velcro, backed with a comfortable cloth, served the best balance between durability and comfort. Finally, to adhere these straps to the mechanical system, we used a series of buckles at the wrist, back plate, and finger strap as shown here. Now I'm going to walk you through the block diagram of our electrical circuit. So first, a varying input force is read in by a force-sensitive resistor. This is passed through a low-pass filter before being sent to the TNC microprocessor. Microcontroller. And this TNC sends out a pulse width modulated signal to the DC motor, which is the vibrational motor. We also have a push button input, which allows the user to cycle through different modes of our device, as well as LED outputs, which show the mode as well as the battery life of the device. So this haptic circuitry is completely battery powered, and it can be recharged using a USB Type-C cable. So our device has three main modes. In the first mode, the strength of the vibration motor is proportional to the amount of applied force at the tip of the prosthetic. In the second mode, the absolute value of the derivative of the applied force at the tip causes the motor to turn on when it exceeds a certain threshold. And in the final mode, the frequency of these vibrational pulses is proportional to the amount of force you're applying at the tip. And so here we have example serial monitor footage of the second mode. And so here we see in blue, the derivative of the applied force spikes up whenever the user grabs or releases an object. And in red, we can see the vibrational motor turning on after each one of these spikes. And so this is an example of how our device can allow for intuitive feedback when interacting with objects. So in order to make our device more lightweight and easily wearable, we miniaturized our circuit using a PCB. This resulted in a 3.4 times area reduction, and now our new board is 2 by 1.7 inches, which is small enough to fit on a user's wrist.
The new mechanical design, improved strap configuration, and miniaturized electrical system all come together to produce our final thumb prosthetic. In our final prototype, I'd like to highlight some important features of our model. First, we focused on a sleek and realistic design by adding curved bars as well as a new strap assembly. Second, our prosthetic is also adjustable in a multitude of ways, including the screws that alter the length of the prosthetic and the straps that add an extra degree of accommodation for every unique user. Lastly, our prosthetic incorporates an advanced technology like haptic feedback in an intuitive way. Little to no training is required to use your device, and with the push of a single button, you can have multiple modes. The next video will demonstrate how our prosthetic can be used to complete everyday tasks. As we continue to develop our device, we hope to expand on its capabilities. First and foremost, we like to conduct patient testing using a custom-made feedback form in order to expose any potential areas of improvement in comfort, design, or functionality. Since many partial digit amputees also have amputations at different fingers, our next steps would be to release a similar prosthetic that was compatible with other fingers. Lastly, we plan to make our device open source in order to make it as accessible to the public as possible. Our device aims to revolutionize the field of partial hand prosthetics by integrating an intuitive mechanical design with sensory feedback technology. Our device goal is to get people back to doing what they love most, including Joe, who can play golf and use chopsticks once again. With Modulo, we bring back function to your fingertips. We would like to thank everyone who has helped put this project together, and we thank you all for listening. We will now open up to some questions.
Hello? Okay. Hi. I love the interdisciplinary nature of all of the testing. You can see where you all contributed from different fields. So I was actually meme and then worked in ESE senior design, so I understand that collaborative nature, but I'm gonna ask a meme question. So you did an FEA analysis, and I like that you took that a step further into a crush test and setting that up, but did you consider any other failure modes like torsion or shear for hitting it against a wall as you're walking by or something like that?
Definitely, sorry about that. We were mainly focused on just the crush test as that is kind of, as it's like a singular hinge, that's kind of where we're going to be applying the most force, but we definitely will, in future testing, we should definitely be monitoring those and we should be able to provide data for those, but I guess for the moment right now, we are only focusing on that crush test, but we'd have to focus on that more in the future. Thank you.
Love the idea. For non-adult patients, I'm just wondering how complex it is to remanufacture this. I know you said it's being created individually, but can you speak a little bit more about it? Pediatrics or somebody with a growing hand?
Yeah, so we actually did talk to some like pediatric rehabilitative specialists, and they did express that because I guess kids is like a whole different realm. The kids are all different sizes, shapes. So for right now, we did focus on kind of that 99.7% of like adults, as they are more standardized, I guess. But in future iterations, we would consider how we can maximize the adjustability to accommodate like different finger lengths and that come with like children.
Yeah, great presentation. Really liked the product. Quick question. So you mentioned obviously that it relies on having residual digit. What are the limitations on that? And for example, what % of the digit needs to remain for accurate function? And how does that compare to actual patient populations in clinical practice for thumb amputations?
So the literature currently on studying the population of especially thumb digit amputees are relatively small. We haven't been able to quantify the exact amount of digit residuum that would be needed, but with the I guess the joint that we're targeting, we would have to maintain that MCP joint. So in order for our prosthetic to be used by a patient, they would need to have that joint in general. So a lot of times, the way that we've understood by talking with clinicians about how these amputees or amputations occur, they often happen with enough residuum to maintain, or they would have lost their entire MCP. So it's kind of one or the other. So we hope that they would have enough residuum in order to accommodate our device.
There's time for another. Hi, beautiful job, guys. My question was along the lines of what Sandeep asked about the applicability to different patient sets. And I noticed that you said you used a force-based sensor. So how does your device calibrate to different levels of ability to generate force, which might be really important thinking of a pediatric patient who has very different strength at age 5 versus like 12 or something?
So right now, basically how the code kind of works is it does like a baseline calibration of how much force is being applied at the start. So basically the proportion of like the applied force to the motor strength is based off of a couple parameters. And so in the future, we would like to give users the ability to sort of tweak these parameters. So that's something that we could look to in the future. So as of right now, these parameters are kind of set. So yeah.